Hey everybody, welcome to Studio 64. My name's David. I've been searching the interzones for more science, space and tech news to share with you and came across this at Interesting Engineering, and interesting it is too. Scientists produce Tokamak plasma that's stable at 10 times Greenwald limit. Future reactor-scale tokamaks will likely need to operate near or above the Greenwald limit. This is absolutely incredible. And as I say, I'm not a scientist myself, but I would love to hear from nuclear chemists, nuclear engineers, fusion experts, would absolutely love to hear from any physicists out there because I love sharing news like this, and I'd really love if you could give your insights into this. This would be incredible. Thank you. Just love sharing news like this. Fascinating. Physicists from the University of Wisconsin-Madison have developed a tokamak plasma that is stable at 10 times the Greenwald limit. Their achievement is expected to have implications for tokamak fusion reactors. However, scientists have cautioned that their plasma is not directly comparable to that in a fusion reactor. It's believed that if net positive fusion energy is ever to be achieved, density is key. The more atomic nuclei crashing into each other, the more efficient the reaction will be. Absolutely incredible. Almost 40 years ago, Martin Greenwald identified a density limit above which tokamak plasmas became unstable, and the so-called Greenwald limit has, at best, been exceeded by a factor of 2 in the ensuing decades. Yeah, as I say, I really am looking forward to when we do get nuclear fusion. I know everyone says, oh, it's just around the corner, it's just around the corner. God, I can't wait for that day till it actually happens. Virtually, I think it's absolutely doesn't produce any waste. It's far more efficient than nuclear fission. Again, not an expert. Just can't wait for this day to happen because it's going to solve a whole lot of problems for us, believe me. Tokamak devices are a leading contender for nuclear fusion reactor. Now, tokamak devices are considered a leading contender in the race to build a nuclear fusion reactor that generates power in the same way as the sun, says Noah Hurst, a scientist with the Wisconsin Plasma Physics Laboratory, or the WIPPL, and lead author on the study. I'm assuming that's Whipple. As I always do, I'll leave the link to the main article below the video so you can pop in, check out the embedded links, go for a bit of a deeper dive if you want. Makes for an interesting read beyond the main article, believe me. Our discovery of this unusual ability to operate far above the Greenwald limit is important for boosting fusion power production and preventing machine damage. Now, the new study, published in Physical Review Letters, is part of tokamak experiments in the Madison symmetric torus with a density of up to an unprecedented level of about 10 times this limit. This is thought to be made possible in part by a thick, stabilizing conductive wall and a high voltage feedback controlled power supply driving the plasma current. Yeah. This Greenwald 10 times limit. If, as I say, love to hear anybody who knows more about it, physicists and stuff like that. Please feel free to drop your comments down because, we'd like to know as a just a science fan community how this relates towards us getting towards, practical nuclear fusion. That'd be great. Thank you. Now, the radial profile of the toroidal. Geez, I can't even speak today. Fascinating. So much of a scientist I am. The radial profile of the toroidal current flattens around twice the limit without the edge collapse routinely observed in other experiments. MST has operated for many years as one of the leading programs studying the reversed field pinch, a toroidal configuration closely related to the tokamak. Now, MST was designed to anticipate operation as a tokamak, allowing direct comparison of the two toroidal configurations in the same device. Unlike other tokamaks, the metal donut that houses the MST plasmas is thick and highly conducting, allowing for more stable operation, according to the University of Wisconsin. Now, my job was to try to find ways to make the plasma go unstable, said Hurst. I tried and find that, well, in many cases it doesn't. It was surprising. Interesting. Researchers looked into plasma density. Now, researchers at the University of Wisconsin looked into plasma density trying to destabilize the plasma by puffing in more and more gas. They set the power supply to provide whatever voltage was needed to maintain a steady 50,000 amps of current in each plasma. As plasma density increases, it becomes more resistive and more voltage is needed to keep the current steady. They measured the achieved plasma density with interferometers, viewing the plasma along 11 different lines of sight. Now, according to the University of Wisconsin, the Greenwald limit is just the ratio of the plasma density to the product of the plasma current and plasma size, a simple metric that allows comparison of different devices and operating conditions. Now, since the limit was defined, only a handful of devices have operated above it, and by at most a factor of 2. Now, future Tokamaks will likely need to operate near or above the Greenwald limit. Here we were at a factor of 10, Hurst said. That's a good leap forward and a good start. Future reactor-scale Tokamaks will likely need to operate near or above the Greenwald limit. So if we can better understand what's causing the density limit and understanding the physics of how we got to 10 times the limit, then maybe we'll have a shot at doing something about it. Now, the researcher also underlined that these results are unlikely to be directly applicable to fusion reactors, such as ITER and others that are being built in the hopes of being the first net positive energy production tokamaks, but he and the team are cautiously optimistic. Now, our results were obtained in a low magnetic field, low temperature plasma, which is not capable of fusion power production. Still, we were the first ones to be able to do this, and you have to start somewhere at it, Hurst. Yeah, that's exactly right. Everything that we take for granted now had to start somewhere. Yeah, look at computing. Yeah, the old mechanical devices of Babbage and all that sort of stuff had to start somewhere. By the way, 1991, I think, was the 200th anniversary of Charles Babbage's, it was his birthday or something, 200th birthday. And some English university guys put together a Babbage computer. This is a side note here. It's just something that fascinates me. And they actually made it, like they rebuilt it, right? And they put through the programs of Ada Lovelace. And they ran 10 times out of 10. Ada Lovelace was basically the first female computer programmer and everything else. Yeah, absolutely fascinating. Loved it. Yes, now, well, back to the land of dreams. Here we go. Now, we're going to keep studying these plasmas, and we think that what we learn might help higher performance fusion devices to operate in the higher densities they need to be successful. Absolutely amazing. Yeah, well, that's a really great step forward, isn't it, for fusion reactor science? I mean, you know, as I say, if you're getting all these little components together, like being stable at 10 times the Greenwald limit, that's a step in the right direction. Now, if we can isolate that, replicate it 100 times, put that experiment aside, get the other components together, get them right, eventually it's got to happen. It has to happen. And I'm one of these people, as I say, I don't know everything about a lot of things, but I know a little bit about a lot, if you know what I mean. I come from a systems analysis background, so I know enough about coding to talk to a programmer and understand what they're saying, though I could never reach their level. You know what I mean? I'm a hardware guy too, because I like to build my own computers. But, you know, I like to speak to guys who do it for a living, and I can understand what they're saying. I can then go and then I speak to a networking guy and understand enough about networking systems to know what they're talking about, even though they know a lot more than me. So then I can come back to all those three components, go hardware, networking, and software, and then sort of translate between the three of them, you know, and able to talk to these guys and say, no, the guy with the hardware is the server, and he's saying that you're going to need a lot more space if you want to do that. And then I can relay to them and say, look, you know, when you're writing your software, your data file has to go into this particular location, et cetera, et cetera. So I can, you know, get a fair idea of, you know, network packet size and talk to the networking guy and say, okay, what sort of throughput are we going to need to get this whole system up and running? So I can get an idea. I'm sort of in the general knowledge of, you know, jack of all trades, you know, master of none sort of thing, you know. And that's why I said I love things like nuclear fusion, being able to break it down into its components and say, okay, we've got this one right. Let's go and talk to the other guys doing their little bit and their little bit, you know, let's see if we can come together as a team and, you know, finalize it. Wouldn't it be fantastic? Can you imagine being the the systems analysis designer, you know, working with people that are much smarter than you who designed the system. And, you know, they're the geniuses that put all the little individual components together. It's like Elon Musk's Starship. You've got the astronauts that pilot it. You got the pilot, you got the commander, you've got the aerospace engineers, you've got the software technicians, you've got all these people from different disciplines coming together for a single goal. And it just blows me away. And when Elon, you know, if he eventually well, hopefully we'll eventually get to Mars, you've got to be looking at other disciplines of science that have to work with them. You know, they've got people that have to, you know, work on, you know, life support systems and, you know, being able to feed and produce water and everything else. So you've got all these, you've got biologists and hydrologists and all working together as a team. And when you look at it, when it comes to things such as, you know, reactor scale tokamaks, you've got all these different disciplines coming together. It just absolutely, I've just got an interest in all those disciplines. It just fascinates me, you know, kind of like, you know, exoplanets, you know, exobiologists and exogeologists and astrophysicists all arguing with each other. But it's so great, you know. We'll finally get to other planets and we'll forget the sandwiches or something. It's something like that, you know. I just, all these different disciplines. I'm just a geeky, nerdy guy who, as I said, looks at all these brilliant people and all their individual disciplines, and they can come together and do something really great. Fascinating, isn't it? All right, well, my name is David. Thanks for joining me for another Studio 64 Science, Space and Tech News update. I shall see you in the next one. If you enjoyed this video, please like, share, subscribe. I'd greatly appreciate it. If you're up for it, drop a comment down below the video because I'd love to hear what you think. All right, take care. And as I always say, if you can't be good at it. And if you're like me and an over-enthusiastic science nerd, as I also always say,
I'll be back.